All right, hello two triggers. Welcome back to school and welcome to day one of remote learning. This is going to be kind of a note-taking video like we would do in class with our PowerPoints, things like that. So if you want to have a piece of paper and a pencil so you can write alongside me, I would recommend that. You are welcome to pause at any time to catch yourself up. Today, our goals are to be doing some more with solving of our trig equations, a thing that we had started in our most recent class, which, almost 2 weeks ago, last Thursday, Friday. Well, 2 weeks ago, Thursday, Friday for you all by the time you're seeing this. We are trying to do some more solving. We're going to use all of our knowledge of right triangles, unit circles, the parent graphs, things like that, but we're going to be doing it with some more complex equations from here on out. So that's the thing we're really honing in on. They're going to get harder. All right, so here is one of our first type. You are welcome to pause the video and try to solve at a time. For this first one, I'm going to walk us through what's going on here. So what we're trying to do is we're trying to solve for this theta between 0 and 360 degrees. So in order to do that, I want to isolate this theta that's right here. The first thing that I can kick over to the other side is that -1 or -1. So I'm going to add that to the other side of the equation. Next thing I can remove from here is that 2. I'll divide 2 over to the other side of the equation. And now I'm left with sine of theta is equal to 1/2. If I was continuing with just straight algebraic solving, I would want to use sine inverse in order to undo that sine. But we all know that that's a calculator maneuver, and we don't need calculator maneuvers because we've got unit circles and parent graphs to help us out. So from here, now I'm trying to figure out where sine of theta is equal to 1/2. We know on the unit circle that, sine of theta is referring to vertical position. So I want to go from here. If this we know is 1, right here smack in the middle is going to be 1/2 at our vertical position. So I'm going to draw a line out. And these would be places where the vertical position would be 1/2. When I say places, what I mean is this angle right here and also this angle right there would be 2 places where the angle value would give us a vertical position of 1/2. So now we're using our knowledge of right triangles. I want to think about what is the angle value right here when I have a vertical position of 1/2, and we know that that triangle has an interior angle of 30 degrees, which tells me that this angle right here is 30 degrees, and that angle right there is 30 degrees. So we can find that our theta value in this case can either be 30 degrees, or it can be 150 degrees using reference angles. Alternatively, we can solve this using our second lens, thinking about the parent graph. From 0 to 1, again, 1/2 is going to be right here in the middle, so I'm trying to figure out where is the output of this graph equal to 1/2. It's not a perfectly straight line, it's a good sketch and an estimate. This needs to stop zooming. But I can decide that right about here and right about here on my parent graph are places where theta would be equal to exactly, sine of theta would be equal to exactly 1/2. And dropping down, again, because of this graph, it's only an estimate, but I know that it's something between 0 and 45 degrees, and another value is going to be between 135 and 180 degrees, which are the 2 values that I had found previously. So, moving from here, everything that we've seen so far is dealing with this given interval, where I tell you where I want the values of theta to fall. However, similarly, I can ask that same question, give you the same equation, but now I can ask you to find all possible solutions. And what happens now with all possible solutions is I don't just want to think about the ones on the unit circle between 0 and 360. I want to think about all of those coterminal angles that would fall at that value or at this place, all of the coterminal angles. Or on the graph, I want to think about any of those intersections right there, not just those first 2. So in order to do that, we just need to think about the coterminal angles that would be at stake. We do already know that this one that's right here and this one right here are 30 degrees or 150 degrees. And if we notice, thinking about either the unit circle or thinking about it on the graph, this 30 degrees we know is going to repeat once every period. So it'll repeat here. It will also repeat right there once every period for our sine function, which is exactly going to be 360 away. So I can either add or subtract 360 degrees in order to move one period away. From there, though, once I get to this point, I can also then add or subtract 360 degrees. and get back to another one. So what I really mean is I want to add or subtract 360k, where k can be any integer. And what I mean by that really is that k can be positive 1, and I'm talking about this point right here. K can be negative 1, and I'm talking about this point right here. K could be negative 27, and I'm talking about some point way off in the distance over there. K can be any positive or negative whole number. And then I have some new coterminal angle that is equivalent to 30 degrees. Similarly, I can do the same for 150 degrees by adding that 360k. I can also think about this on the unit circle. If right here, this is 30 degrees, well, this one is 360 plus 30 degrees, or this one is negative 360 plus 30 degrees. There are lots and lots and lots of coterminal angles that all end at this point, and this is the way that we denote them. So if we're asking for all possible solutions, we have a little bit more notation that's involved. From here, however, our problems only get trickier. Oh, that graph showed up a little early, but that's okay. So what I'm going to ask you to do is pause the video at this moment, attempt to solve this one, and then play once you've finished so you can see the solution. All right, now that you've finished your solving, let's talk through this. So if you notice in this equation, I've got sine of theta is equal to negative 2 times cosine of theta times sine of theta. My gut tells me that there are two different things that people did from here in order to solve. I've got sine of theta and thetas on both sides of this equation, and I don't really like having them there. So I want to move everything so that theta is on one side of this equation so that it becomes more simplified, so I can isolate theta all on its own. In order to do that, I want to move this sine of theta. Now there are two things we can think about to do to move this sine of theta. I can either subtract sine of theta, or I can divide by sine of theta. If I subtract sine of theta, I can subtract literally any number from any number. Never in the world of math, well, I don't want to say never, but in the world of math, that doesn't actually lead to us having problems. However, if I divide by sine of theta right now, dividing gets a little bit hairy, especially when you start dividing by weird numbers. The number that I'm referring to really right now is 0. If I divide by 0, the math world shatters a little bit. And right now, I'm not confident that that sine of theta, that expression right there, isn't equal to 0. So in order to prevent myself from breaking the world of math, I don't want to divide by sine of theta. Instead, I want to subtract sine of theta over to the other side. We are technically adding it to 0 right now in this moment, so I'm going to subtract it to the other side and I'll just be left with 0. But this is to guarantee that I don't end up doing something that's breaking a math rule, meaning dividing by 0. Okay, so now I have everything that's involving theta on one side of the equation. It looks a little bit more concise, but now I've got two terms that are both being subtracted. If you notice, in both of these terms, there is a sine of theta involved. So I'm going to factor that out in front. So if I factor out sine of theta from that expression, what I'm left with is a negative 2 cosine of theta in that first term. And in that second term, I'm just left with negative 1 as my placeholder. It is still, of course, equal to 0. The 0 on the other side of the expression did not disappear. And now from here, I have two terms multiplied together, two factors multiplied together equal to 0. I am not a fan of this zooming. So what I can use from now is the zero product property and say, well, either sine of theta was equal to 0 all along, or negative 2 cosine of theta minus 1 was equal to 0 all along. And from here, sine of theta equals 0, we could solve right away, thinking about that sine of theta is referring to vertical position, where when my vertical position turn out to be 0, well, that means that I'm seated right there on the x-axis. So that, for me, would mean that theta is either 0 degrees or 180 degrees, or because of the things that I'm talking about between, technically 360 degrees. For cosine of theta, there's a little bit more solving that I've got to do. From here, I want to continue to isolate cosine. So I'm going to add 1 to the other side, then I'm going to divide by that -2. And now I want to know where cosine of theta is equal to 1/2. We know that cosine of theta is talking about horizontal position. So in this case, horizontal position being -1/2 would be referring to this line right here, horizontally. That line right there, horizontally. So in order to find those, I'm referring to this angle and that angle that are right here. This one and that one. Now the triangle that exists where, oop, that's not the triangle I mean. Sorry. The triangle, goodness, technology is being difficult for me today. The triangle that exists where this value, the horizontal position, is 1/2 is when we've got an interior angle of 60 degrees, which is then my reference angle. So I can find that theta is equal to 120 degrees or 240 degrees. Similarly, I can double check these values thinking about the graphs of the two things. I'm realizing right now in this moment that I don't have the parent graph of cosine queued up, but I've got it for sine right here. I want to know where sine of theta is equal to 0 degrees, so I'm trying to find those intersection values, which we can see very clearly. If I quickly graphed out what cosine looks like, here's 0, here's 360, here's 180 in the middle down at -1, here is 90, here's 270. This is what cosine of theta looks like in its sketchiest version. That's a 360, not a 36. So with that in mind, then I also would want to be thinking about where this -1/2 would occur. And those two values we can trace back to 120 degrees and 240 degrees, respectively. All right, from here, things get grosser yet again. I'm going to flash this equation. This equation reads 2 sine squared x minus sine x plus 3 equals 4. But wait. I'm lost. I'm stuck. I'm confused. Sine squared of x. What the heck is that talking about? We know that sine is a function, not a number. So how the heck can we be squaring this function? It turns out old mathematicians a way long time ago made up this notation to imply that they are taking the value of x, applying the function of sine to it first, and then squaring that output. So what we really mean is when we say sine squared of x, what I mean is sine of x squared, using that breathing to help denote grouping symbols as I do. However, I want to be really clear that this is not the same as squaring the inputs. These two things are not the same. Sine squared of x is very different and not at all equivalent to sine of x squared. Those are two different equations, and I want to be really clear about that. So when I say sine squared x, what I really mean is I took the value of sine of x, took that output, and then squared it. Okay, so going back to that crazy equation, if I've got 2 sine squared x minus sine x plus 3 equals 4, this equation is a monster. From here, I'm going to give you one little hint. I don't know why those keep showing up at the same time. There's my hint. Pause the video at this moment. See if you can try to solve for yourself with that hint in mind. Okay, now that you have officially tried to solve yourselves, let's talk about it. If I've thrown in those little blobs, what I mean is we're back in quadratics land. Oh yes, friends, your favorite place to be, quadratics. So I've got 2 blob squared minus blob plus 3 equals 4. For quadratics, we always wanted everything set equal to 0 so we could use that zero product property or the quadratic formula if need be. In order to do either of those things, what I needed to do is I need to move that 4 over to the other side. So I've got 2 blob squared minus blob minus 1 is equal to 0. And now I gotta factor this bad boy. So I need to think about my factoring area model. I'm gonna place my 2 blob squared and my -1 right away. Refresh yourself. First term is always the first 2 together. Last term is always the 2 constants together. we're trying to figure out what middle two things add up to give me -1 as far as the blob is concerned, and how they multiply to give me -2. So what two terms give me that? Well, it would in fact be -2 and +1. So I can place a -2 blob and a +1 blob in as so. You can switch the order if you did, no big deal. And then I want to factor out to see what's common along each row and column. So along this first column, columns, rows, hard for me to do. Along this first column, there's a 2 and a blob in common. And along that second column, they have a measly 1 in common. Along the top row, those two terms have a blob in common. And along that bottom row, they have a -1 in common. So from here, I've created some factors. 2 blob plus 1 and blob -1 are now equal to 0. From here is the moment where I would like to remind you that blob is not actually what we are dealing with. What we are instead dealing with is sine of x. So I've got sine of x replacing both of these blobs. And again, from here I'm going to use zero product property, our BFF, to help us continue to solve. So now, either 2 sine x plus 1 equals 0, or sine x minus 1 equals 0. So sine x minus 1 is the same as saying sine of x equals 1. And again, now I'm referring to the vertical position on the unit circle, and where that is going to be a +1 is right here at 90 degrees. Similarly on the graph, where is it +1? Well, they intersect right here, again at 90 degrees. For 2 sine x plus 1 equals 0, I got to do a little bit more solving. So now I need to think about the vertical position where that's equal to -1/2. So I'm referring to this place right here, or these two angles. Again, I'm going to draw my triangle thinking about where this vertical position is 1/2. I've got an interior angle of 30 degrees. So that tells me that using that 30 degrees as my reference angle, I've got 210 degrees or 330 degrees. Similarly, on my parent graph, I can draw a line right here at -1 and find those two intersections. Okay, great. There's our 3 different types of solvings that we're going to be working with today. So here's my last thing that I've got for you. We're referring to this as an entrance ticket for now, similarly to how we do exit tickets in class. However, it's going to be your entrance ticket into our class period as you are watching this video before class is happening. So you are going to try to solve this equation between 0 and 360 degrees. Complete this on your own paper. Write it out, actually, not just the answer. Write out your solving steps, and then head over to Google Classroom. Find the survey that your teacher has posted so that you can submit your solutions, as well as any questions that you've had about this video, and we will address those during our class period block throughout the week. All right, see you later, Triggers. Bye.